Section 5.5, the Fibonacci sequence and the golden ratio. The Fibonacci sequence was developed by Leonardo of Pisa. He lived from 1170 to 1250. The sequence is a sequence of numbers where after the first two terms, the next term is obtained by adding the previous two terms. There's a rabbit problem that is a famous Fibonacci sequence problem. A pair of rabbits have no offspring during their first month of life, but produce one pair of offspring after each month thereafter. Starting with one newborn pair of rabbits, how many pairs will there be after the 12th month? So the first month, there is one pair of juvenile rabbits, 0 pairs of mature rabbits, and 1 pair of rabbits total. The second month, there are 0 pairs of juvenile rabbits, 1 pair of mature rabbits, 1 pair of rabbits. The third month, that 1 pair of mature rabbits has 1 pair of juvenile rabbits. Still have that 1 pair of mature, and now we have 2 pairs total. The fourth month, that 1 pair of mature rabbits has 1 pair of juvenile rabbits, but now that juvenile rabbit pair from month 3 becomes mature, and now there are 2 pairs of mature rabbits, 3 pairs total. Of those 2 pairs of mature rabbits, there are 2 new pairs of juvenile, and then there are 3 pairs of mature. Total 5 pairs. Those 3 pairs of mature rabbits in month 6 give us 3 pairs of juvenile rabbits. We had our 3 pairs of mature, our 2 pairs of juvenile, 5 pairs, total 8 pairs. Our 5 pairs of mature give us 5 juvenile. We now have 8 pairs of mature rabbits, and we have 13 pairs of rabbits. Those 8 pairs of mature rabbits give us 8 pairs of juvenile rabbits. We now have 13 pairs of mature rabbits, 21 pairs total. 13 pairs of juvenile, 21 pairs of mature, 34 pairs total. 21 pairs of juvenile, 34 pairs of mature, and 55 pairs total. 34 juvenile, 55 mature, 89 total. 55 juvenile, 89 total mature, 144 total pairs of rabbits. Looking at that total pairs of rabbits column, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. The first 12 Fibonacci numbers are 1. The first one is 1. The second one is 1. Third one is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 34. 34 plus 21 is 55. 55 plus 34 is 89. 89 plus 55 is 144. The Fibonacci series is developed through a recursion formula, where our first number is 1, our second number is 1, and then our next term is found each time by adding the 2 previous numbers. Patterns in the Fibonacci sequence, summing the squares of the first n terms. The first number squared, 1 squared, which equals 1. The first number squared plus the second number squared is 1 squared plus 1 squared, which equals 1 times 2. The first number squared plus the second number squared plus the third number squared is 1 plus 1 plus 4, which equals 6, which can be written as 2 times 3. Squaring the first 4 Fibonacci numbers and adding them, the sum is 15, which is 3 times 5. Summing the first 5 Fibonacci numbers, the sum is 40, which is 5 times 8. Remember that the 5th Fibonacci number is 5, and the 6th Fibonacci number is 8. The 4th Fibonacci number is 3. The 5th Fibonacci number is 5. The 3rd Fibonacci number is 2. The 4th one is 3. The first Fibonacci number is 1. The second one is also 1. The sum of the squares is f sub n times f sub n plus 1. It's the Fibonacci number that you're on times the next Fibonacci number. Ratios of successive terms in the Fibonacci sequence. The second number divided by the first. 1 divided by 1 is 1. The third number divided by the second is 2. The fourth number divided by the third. 3 divided by 2, 1.5. The fifth number divided by the fourth. 5 divided by 3 is 1.6, repeating. The sixth number divided by the fifth is 8 divided by 5, which is 1.6. The seventh divided by the sixth is 13/8, which is 1.625. The eighth divided by the seventh is 21 over 13. It's 1.6153. The ninth divided by the eighth, 34 divided by 21, 1.619. The 10th divided by the 9th, 55 over 34, is 1.6176. The 11th divided by the 10th, it's 89 divided by 55, which is 1.61818. The 12th divided by the 11th, it's 144 divided by 89, which is 1.61797. And the 13th divided by the 12th is 233 divided by 144, which is 1.618055. Looking at these ratios, you can see that they're all very close to 1.61 as we get further. The ratios approach the golden ratio. The quotients seem to be approaching some Libby value, close to 1.618. Continuing further with the calculations, the quotients approach the golden ratio. The golden ratio is 1 plus the square root of 5 divided by 2. The golden ratio appears in art, architecture, music, and nature. Golden rectangles have the property that it can be divided into a square and another smaller rectangle with the same ratio of dimensions as the original rectangle. Okay, the whole thing has the length a plus b. The square part is then a times a. The length of the rectangle is a plus b. The logarithmic spiral in nature. Spirals are made when the vertices of a square are joined with a smooth curve. It is an example of the golden ratio. As successive squares are made. As section 5.5, the Fibonacci sequence and the golden ratio.